So let's take a look at another example. In this example here, we have a structure with a mass of 10 kilograms, a stiffness given to us is 40 kilonewtons per meter, and a damping factor of 0.1. This is subject to a harmonic force of amplitude 500 newtons and a frequency of 15 radians per second. Now they also give us that f of t is equal to 500 times the sine of 15t, and they give us our initial conditions. U naught, our initial position, is equal to 6 centimeters, and V naught, our initial velocity, is equal to 0. They ask us to find a couple different things. One, they want us to find the amplitude of steady state displacement. Two, we need to find the phase relative to the exciting force. And three, we need to find our equation of motion. So now that we've had a chance to read through that problem statement, the next thing we want to do is create our setup page. So we have our heading up top there, ME270, Lecture 401, example problem. What do we have given to us in the problem statement? Well, they gave us a lot of information. We didn't have a given diagram this time, but we did have variables with values. So we knew our mass was 10 kilograms. Our spring constant was given to us as 40 kilonewtons per meter. So I'm instantly right here going to convert to newtons per meter. That's typically what I use. I don't have to worry about doing that as I'm going through the solution of the problem. I can just quickly reference back to the setup page and pull it right from here. My zeta, my damping factor here, is 0.1. P naught is given to me as 500 newtons. We have the frequency of 15 radians per second here. We have our f of t relationship given as 500 times the sine of 15t. We have our initial conditions now here. Our U naught is equal to 6 centimeters and our V naught is equal to 0. Again, they'd asked us to solve for the amplitude of steady state displacement, the phase relative to the exciting force, and our equation of motion. So the next step as we begin our solution is to go through and figure out what key equations we're going to need in order to solve for the components to get us to what they ask us to solve for in the problem statement. So one of the things we realize we're going to need is our natural frequency. Now we have a relationship for our natural frequency. Omega sub n is equal to the square root of k over m, where we have our k value, which we've already converted to newtons per meter, as 40,000 newtons per meter, and our m value given to us as 100 kilograms. So we can plug that back in here for our k and m. When we do that, we end up with the square root of 40,000 over 100, or our omega sub n, our natural frequency, is equal to 20 radians per second. We also realize we're going to need an r. So this comes back to equation 4.6 on our textbook, where r is equal to our omega over our omega sub n, where we're given our omega term, 15 radians per second. Our omega sub n we just solved for above here is 20 radians per second. So we can plug that back into our frequency ratio equation here, 4.6. We end up with 15 over 20, or r is equal to 0.075. Now the next thing that we're going to need to do is come up with our static displacement. So for our static displacement, we go back to equation 4.4 on page 82 of our text. Our U naught is equal to P naught over K, where our P naught is given to us as 500 newtons. And our K is given to us, again, once we convert to newtons per meter, of 40,000 newtons per meter there. Plug these two values into equation 4.4. We end up with U naught is equal to 500 over 40,000, or U naught is equal to 0.0125 in units of meters. So if we reference back to either our problem statement or our setup page, we realize that the first thing that they asked us to solve for was a steady state amplitude. Now we have a governing equation here from our text for our steady state amplitude, where U is equal to U naught divided by the square root of 1 minus r squared plus 2 zeta r squared. Where now we have a value for r, we have a value for U naught. Our damping factor was given to us in the problem statement. So we can plug all those in. Our U naught is equal to 0.0125 meters that we just solved for. Our r we just solved for is 0.75, and our zeta term is 0.1. So we can take these values and plug back up into our steady state amplitude equation here for our r, U naught, and zeta terms there. We do that, and what we end up with is U is equal to 0.0125, our U naught, divided by the square root of 1 minus our r squared, entire quantity squared, plus 2 times our zeta term there, times our r term, quantity squared. We do out the math. We end up with u is equal to 0.027 in units of meters. So the next thing we need to solve for in our solution here is our phase angle. So we have this relationship here that the tangent of our alpha term is equal to 2 times zeta r over 1 minus r squared, which we can plug in our known values. We have our zeta term that what we have in our problem statement is 0.1, our r term that we found to be 0.75, and 0.75 down there. Plug those values in from our knowns. Solve this for alpha, so alpha is equal to inverse tangent of 2 times 0.1, our zeta term, times 0.75, our r term, over 1 minus our r term, 0.75 squared. Plug that in, what we end up with is that our alpha term here is either 0.33 in radians, or if we convert to degrees, 18.908 degrees. So what we want to do next is find our total response equation. So this comes from equation 4.24 on page 90 of our textbook. So here is that total response equation. U of t is equal to u naught divided by the square root of 1 minus r squared plus 2 zeta r quantity squared times the sine of omega t minus alpha. So this is where we're going to use that alpha we just solved for, plus the second half of this, e to the negative zeta omega sub n t times a1 times the cosine of omega d plus a2 times the cosine of omega d times t. So we have this new omega d here. We have our a1, our a2, in terms of time, we have our t's throughout this as well. We already know we have our r's and zeta terms and omega terms there, and we now have an alpha, and we also have our u naught. So let's figure out exactly what we have and what we need to solve for. So I write out everything I know down here because we got a long involved governing equation up here. We know our u naught is a known value of 0.0125 meters. Our r we found to be 0.75. Omega is given to us as 15 radians per second. Our alpha we just solved for, so if we leave this in radians to keep track in line with everything else, we have this as 0.33 radians. Our zeta is given to us as 0.1, and our omega sub n, our natural frequency, is 20 radians per second. So we can solve for our omega sub d from what we have here as omega sub 1, and our zeta term, so omega sub d is equal to our omega n times the square root of 1 minus our zeta term squared, or 20 times the square root of 1 minus 0.1 squared, which ends up being 19.9 radians per second for our omega sub d. So we can take all of these known values and plug back in up here to reduce and simplify. So we do that there. We plug back into this governing equation there. And we end up with is u sub t is equal to 27.025 times the sine of 15t minus 0.033 plus e to the negative 2t times a1 times the cosine of 19.9t plus a2 times the sine of 19.9t. So this is reduced and simplified with all of our known values here plugged in to that total response equation. So next, we want to apply our initial conditions. So they give us the fact that our initial position, our u naught, is equal to 6 centimeters, and our initial velocity, v naught, is equal to 0. So we can plug those in. So initial conditions imply that we're dealing with time is equal to 0. So we can plug in a u of time equals to 0 into that governing equation from the previous page there. And we can see here, this is equal to 27.025 times the sine of 5, plug in our 0 for t there, minus 0.33, plus e to the negative 2, plug in a 0 there, and then we have a1 times the cosine of 19.9t, plug in a 0 there, plus a2 times the sine of 19.9t, plug in a 0 there. And when we do that, this reduces down. We have u naught is equal to 27.025 times the sine of 0 minus 0.33, plus e to the 0, which becomes a 1, times a1 times the cosine of 0, which becomes a 1, times a2 times the sine of 0, which becomes 0 there. So we're left with u naught is equal to 27.025 sine of negative 0.33 plus a1. Plug in our known value for our initial condition, 60 millimeters for u naught is equal to a1 minus, when we do our math out here, 8.76, or a1 is now equal to 68.75. So from the initial conditions and our u of t, we were able to come up with a value for a1. So now that we were able to use one of the initial conditions in order to solve for our a1, the next step is to solve for our a2. And in order to do that, what we're going to do is take the derivative of our u of t function so that we can plug in our v naught or our u dot of 0 here. Because we have a value for that. We recall that v naught is equal to 0, so our initial velocity is 0, or u dot of times 0 is equal to 0, again from those initial conditions. Plug that back in. We can take the derivative of that equation. I'm not going to do all the steps for the derivative here. Same as we've done in the previous problems, take the derivative of our u of t function, plug in a value of 0 so that we now have a u dot of 0. We do that, we end up with 383.5 minus 2a1 plus 19.9a2. So we have two unknowns, one equation, but technically this is a known because we just solved for that when we were other initial condition for initial position. Do that, plug in our value for a1 from the previous page. We end up with our a2 is equal to negative 12.36. So for our total solution, we can plug our a1 and our a2 values back into our u of t equation here from our initial conditions that we solved those for. And u of t is equal to 27.025 times the sine of 15t minus 0.33 plus e to the negative 2t times 68.76 times the cosine of 19.9t plus 12.37 times the sine of 19.9t is our total solution.